10. Okay. So to start with, we'll start with the MCQs. Number 1, in the balanced molecular equation for the neutralization of sodium hydroxide with sulfuric acid, the products are, we've already been given the reactants. All we need to know is how to write their chemical formulas. And we are using sodium hydroxide, which is this one, and it's reacting with sulfuric acid, which is this one. When this reacts, the sodium will react with the sulfate, so forming sodium sulfate. The 2 from the sulfate will come here because the radical sulfate has got a valence of 2, and then also form water. Is the reaction balanced? No. We're supposed to put a 2 in front here. If we put a 2 in front here, we have made the hydrogens to be 4, so we're going to put a 2 in front of water. So that is going to be the product. Which one is that? That is a D, isn't it? Okay, so that is it. Be very free to ask, please. You shouldn't go off the class without you understanding anything. The mass in grams of 2.6 times 10 power 22 chlorine atoms is, we want the mass in grams. Okay, the first thing is we need to find the number of moles. Now I've been told we've been given 2.6 times 10 power 22 chlorine atoms. One thing you need to know is that 1 mole of something is equal to 6.022 times 10 to the power 23 atoms, particles, molecules, ions, and everything like that. This is the Avogadro's number. Now we want to find how many moles are in this number of atoms, which is 2.6 times 10 to the power 22. So all we do is we're going to cross multiply and find the value of x. So x will give us, I'll multiply 1 by 2.6 times 10 power 22. So that will give us that same number. I'll multiply x with that number, which is Avogadro's number, and then to remain with x, meaning that I'll divide both sides by the same 6.022 times 10 to the power 23. So all I'm going to do to find the number of moles is divide 2.6 by 6.022, and that will give us like 0.43175. This is 10 to the power 22, this is 10 to the power 23. We know according to the laws of indices, when we are dividing numbers of the same base, just subtract the power. So that will be 22 minus 23. So this will be times 10 to the power negative 1, which means that x actually is 0.043175. These are the number of moles. This is chlorine that has been given. The mass in grams of 2.6 chlorine atoms is that. So now I want to find the mass in grams of, okay, we've been given the atoms. Now I want to find the mass. How do you find mass when you know the number of moles? Mass is number of moles times molar mass. The molar mass of chlorine is like 35. So just multiply this number by the molar mass of chlorine, which is like 35. And that answer that you are going to find is going to be 15.11 in grams. So which one is going to be the answer here? This is 1.5, 0.76, 11, 4.4. Okay, let me do something. What have I missed out? Okay, I forgot to multiply by a certain number. Yeah, just give me a moment. When I was multiplying on my calculator, I didn't use 0.04, I used 0.4. So I was supposed to divide this number by a 10. This number which was on top here, 0.43, by a 10 to give me the one which is at the bottom. So the value that I've gotten is 1.51 grams. So that is D. Is this making sense? Are we all moving together? Now, that's why I would rather record a class and post than in a class and then you are talking alone, you're asking people as though they are not listening to you. Anyway, I'll just be solving, I'll not be asking since you don't want to answer when I say. So if you've not gotten it, you stop me. I'll not be asking. Okay. Question 3. A real gas most closely approaches the behavior of an ideal gas under conditions of. A real gas mostly approaches the behavior of an ideal gas under the conditions of high pressure and temperature, low pressure and temperature, low pressure and low temperature, high pressure and high temperature. Now the first thing we need to understand is what is what properties are there for an ideal gas? What properties do ideal gases follow? When you are talking about an ideal gas, it's just an imaginary gas, what we are saying. Okay. An ideal gas is a theoretical gas, and ideal gases will obey the Bohr's law. Don't know if that's a spelling. And this law is getting to relate to us pressure, and also you've got the Bohr's law, the Charles law, and those others which are relating pressure and volume, pressure and temperature being inverses of each other, and like that. Mostly when you are at low temperature, low pressure, give me a moment, a second, please. Okay, just linger a bit. Within 30 seconds, I'll be done. Okay, sorry for that. Sorry for that. You can still see? Hello, are you able to still see what's there? Okay. All right. So we are saying a real gas most closely approaches the behavior of an ideal gas under conditions of, all saying that real gases mostly for ideal gases, these are just hypothetical gases. They are going to follow the Charles law, obey the Bohr's law and all those. Now a real gas might not necessarily get to obey these laws. So for a real gas, it is going to approach the behavior of an ideal gas when the pressure is becoming low and the temperature is becoming very high. Mostly because these two guys are opposites of each other. When you increase the temperature, you are trying to reduce the pressure like that. Okay. The relationship between them, if you use actually P times V over T, if you know that equation, PV over T is equal to PV, P1 V1 over T1 is equal to PV V2 over T2, the ideal gas law. So you are increasing temperature, reducing pressure, then you are approaching the behavior of a real gas. Now the next question is saying, which of the following electromagnetic waves has the highest frequency? The electromagnetic waves, you need to know the order of how they do move, starting with the one with the highest frequency to the one with the lowest frequency. Actually, the frequency will go together with the wavelength, just that for wavelength is going to be opposite to the frequency. So let me write that. Okay, so the one which has got the smallest frequency is the X-ray, and then this is going to be followed by, actually not the X-ray, but you are going to have gamma radiations, GXUV, visible light, and then you should have infrared, microwave, and radio wave. So coming from this direction, going in this direction, you are increasing the wavelength. You are reducing the frequency because wavelength and frequency are opposites of each other. Okay, take note of that. Wavelength and frequency are opposites of each other. So of these ones which are given, which one do you think is going to have the highest frequency? From what I've already mentioned. Which one is going to have the highest frequency? Are you here? Are you following here? There's something that you're doing? So as you are going from gamma radiations have got a very small wavelength. So wavelength increases going in this direction, while frequency increases as you go in this direction. So now we are determining which one has got the highest frequency here. Do you get it now? Yes, gamma rays. I want you people to speak because some of these things you will not remember them not until you speak. Okay. Okay. The table below shows the color of light emitted when an electron in hydrogen atom uh, transitions at a certain wavelength. What color of light is emitted when What color of light is emitted when electrons in the hydrogen atom fall from n is equal to 5 to n is equal to 2? They've already given us the wavelengths here. Now, also told us that an electron moves from n is equal to 5 to n is equal to 2. How do you determine that? You need to find the wavelength of that photon or that light that is emitted. And wavelength is given by, uh, we actually don't find wavelength direct. We'll find it as an inverse using the Rydberg equation. 1 over wavelength is given by RH, that is 1.097 times 10 to the power. What is that power? You can remember, but this should have been given in the question. It's not something that you should master anything. Okay. Okay, the value is here. 1.097 times 10 power 7 times 10 to the power 7, and then we say 1 over, inside the brackets, actually the formula is 1 over wavelength is equal to RH, 1 over the final energy level squared minus 1 over the initial energy level squared. And the final energy level, we are going to the second energy level from this question. So that will be 2 squared minus 1 over, we're coming from the fifth energy level, so that will be 5 squared. 1 over 2, 4, 1 over 5, 25. So we are saying 1 over 4 minus 1 over 25. 1 divided by 4 minus 1 divided by 25. The answer we get, will now multiply it by 1.097 times 10 to the power 7. So that will give us 1 over wavelength being equal to 2303700. For me to find the value of the wavelength, I need to find the inverse of this number, or I will simply say this is over 1. I cross multiply and then make this the subject the formula. So we're going to say just the inverse of our answer. The answer that we have found, to the power negative 101 divided by 23037, and that is going to give us 4.34 times 10 to the power negative 7. So answer that you punch is in meters. If you convert this number to nanometers, you are going to get wavelength being equal to 434 nanometers. All you do is multiply this number by 10 to the power 9. Okay, you would have converted to nanometers. So from what you can see, what color do you think this one is going to show? What color? Okay, color blue. Generally, across a period of the periodic table from left to right, the first ionization energy increases. This is due to, now ionization, what is ionization energy? Ionization energy, look at this. If you have got an atom X, it becomes an ion. So it is X plus an electron. So what have you seen? It has become an ion. How has it become an ion? It has lost an electron. So that is what we refer to as the ionization energy. By definition, ionization energy is the energy that is required to remove an electron from a gaseous atom. The first ionization energy is the ionization energy required to remove the first electron. All right. And this energy is going to increase as you get to move in the periodic table from left to right, generally, as we've been told. And what will be the reason for that? First, ionization energy. Let me first mention this. The increase in positivity of charge. When you are moving from the left, let's say we are talking about atoms which are this position in the periodic table, and then we are going in this direction. What is happening to the charge is that the charge is increasing. So the increase in the positivity of charges bind electrons more firmly, and the ionization energy increases. What I'm saying is this: think of it, an atom that is, let's say, let me give an example of an atom that is in group 1. An atom that is in group 1 has got an effective nuclear charge of positive 1. An atom that is in group 7 has got an effective nuclear charge of positive 7, meaning that electrons in group 1 are one time more stronger bound to the nucleus. Electrons in group 7 atoms are 7 times more bound to the nucleus. Ionization energy is the energy that is required for you to remove the electrons. So, between something that is one time bound to, and compared to something that is 7 times more bound, which one is going to be hard for you to remove? It's the one which is 7 times more bound. So, that makes as you go from left to right in the periodic table, the ionization energy to increase. Why? Because you are increasing the binding. So for you to be able to separate the electron from the atom, you need more energy. Okay, so what is the answer? It is increase in effective nuclear charge. Okay, question 7. Which of the following violates the octet rule? Violates the octet rule. To find out which one is going to violate the octet rule, let's start. Mostly those which violate the octet rule will be those atoms which are in group, like group 3, group 2, group 3, where you have got especially where there is phosphorus. Violates octet. Let's find out, for example, PCl3. What you are interested in is looking at the valence electrons. Valence electrons are electrons in the outermost shell. Phosphorus is in group 5, so it has got 5 electrons in the outermost shell. You have got 3 chlorines, each is in group 7, 7 electrons in the outermost shell. 3 times 7 is a 21, 21 plus 5 is a 28. So when I want to draw the Lewis structure for phosphorus trichloride, I'm going to write phosphorus with the 3 chlorines around. Each bond that I've used here carries 2 electrons, meaning I've used 6 electrons. So from the 28, I've used 6 electrons, meaning that only 22 electrons are remaining. And then the next thing that I'm going to do is I want to make sure that each chlorine has got 8 electrons in the outermost shell. So of those 26, I am going to put 6 electrons here, and then they have become 8. 6 electrons there, 8. 6 electrons there, also 8. So of the 26, I've removed 6 times 6 times 6, I mean 6 plus 6 plus 6, that is 18. So 18 from 22, how many are we remaining with? We are remaining with 4 electrons. Those 4 electrons, where are they going to be? They are going to be on phosphorus. As this balance octet, let's look at phosphorus. 2 electrons here, 2 there, 2 here. So 2, 4, 6, 8, 10. You can see that phosphorus has got more than enough electrons. It has got actually 10 electrons in the outermost shell. So it has violated octet. Mostly atoms in group 3, okay, of the periodic table. I mean period 3, not group, where phosphorus is. They violate octet. Also, atom like is it this one, boron, can also violate octet by having incomplete octet. These ones will have expanded octet because they have more than enough, but they are stable. So the aim of chemical reactions is not just to attain octet or do it, but to attain stability. Okay, let's go to the question 8. The half-life for a first order reaction is 32 seconds. What was the original concentration if after 2 minutes the concentration is 0.062? The thing for us to be able to answer this question is we need to know the formula for the half-life of a first order reaction. Now, let's first find out the data that we've been given here. We've been told the half-life, let me write that, T half is 32 seconds. What was the original concentration? Meaning we want the initial concentration, and that is what we don't know. After 2 minutes, so the time that should pass is 2 minutes. What is the original concentration if after 2 minutes the reactant concentration is? So the concentration after 2 minutes is 0.062 molar. Okay. The half-life of a first order reaction. Can I ask anyone who knows the half-life of a first order reaction? Any idea? Okay, this is what you need to know. Please, you need to make sure that the formula for half-life of a first order reaction, uh, second order reaction, and also zero order reaction is in your head. Otherwise, you are going to find it hard if you don't know those. Okay, so to start with a first order reaction, let me start with a zero order reaction, its half-life. Maybe let me ask a simple question, because sometimes if you've forgotten the formula, you can actually get the equation for half-life. How do you define half-life of a compound? How do you define half-life? Anyone who has got an idea? Are people even in class? How do you define half-life? Anyone? It's not to trouble you. I want you to I know the importance of this. I've been teaching this. So anyone? You are just alone in the class, Ezra. So you are the one I'm asking. Do you have an idea? Life. You can't get me? So I was saying I didn't get what you said. On the zero order, what did you say? Okay. No, I got you for the first order. So I was asking, do you know for the zero order reaction? Mm-hmm. Uh-huh. Okay. So these three that I've written here, please, it's a must know. It's a must know when you are going to write your exam. Okay, for a zero order, half-life is only dependent on the initial concentration and the rate constant. For a first order, what did you say for the first order? What did you use? You use natural log of 2. You can actually use also a number. Which one do you know yourself? Natural log? That's the one you know. Okay, in that case, if that's the one you know, I'll advise you stick to that. So natural log of 2 divided by k. And then for a second order reaction, the half-life is going to be 1 divided by k, initial concentration of, isn't it? So this is a question they can also give you in multiple choice. A zero order is dependent on the concentration of the reactant, the initial concentration, and also the rate constant. First order reaction does not depend on the concentration of the initial concentration, okay, as you can see from here. While a second order would depend on the initial concentration and everything. So we've been told that the half-life is 32. So we'll come and substitute because they've told us this is a first order reaction. We'll come and substitute here. Where there's half-life, we'll put 32. And that should be equal to natural log of 2 divided by k. So your aim is to find the value of k. So to find the value of k, it will just be natural log of 32 and natural log of 2 divided by 32. If you have a calculator, you can help me to punch that real quick. Natural log of 2 mhm, divide by 32. 0 mhm, 62166, isn't it? So this is the rate constant. And then the question is asking us what was the initial concentration. We want to determine the initial concentration. We've been given the final concentration being a 2, and then we've been given after. We got that concentration after 2 minutes. So for you to be able to find the initial concentration given this information here, you need to know the integrated rate law. Okay. So again, apart from you knowing the half-lives, which I've written here, for a first order, a zero order, a second order, you need to know the integrated rate law. Very, very important. So I'll keep the rate constant here because we'll use it. Starting with the zero order reaction, its integrated rate law is going to be given by the final concentration is equal to the initial concentration minus kT. That's for a zero order reaction. First order reaction, natural log of the final concentration is going to be equal to the natural log of the initial concentration minus kT. For a second order reaction, let me write it here, second order. The integrated rate law is 1 over final concentration being equal to 1 over initial concentration plus kT. It's only second order that has got a positive gradient. The others, you can see it was minus, minus. So we want to use now this formula here. So I'm going to say natural log, the initial concentration we are given, I mean the final concentration, because we are using this formula. After a time of 2 minutes, the concentration was 0.06. So that is 0.062. And this should be equal to natural log again. Initial concentration is what we are trying to find. So I'll just put A there with an O. And then minus kT. K, the rate constant, is 0.02166. The time, this was after how much time? After 2 minutes. Now we want to use time that is in standard units. So we're going to use that in seconds. 2 minutes is 120 seconds. So let's start to punch. First thing I want you can punch natural log of this number. Okay, so what I'm going to do is, let me start this side because I already know 0.02166. I'll multiply it by 120. And then the answer that I'll get, I'll take it this side so that I add it to the natural log. So the answer I get, I'll add to natural log of 0.062. The answer that we are going to get, so now what I'm finding here is, remember this side we have remained with natural log. So natural log of initial concentration is going to be equal to, the answer that I'm finding is a negative 3.382. Remain with A here, which is the initial concentration. Natural log is in base E, so it will be E to the power negative 3.382. So natural E to the power negative 3.382, and that is giving me a 0.033979. 0.033979. Which one is that? So of these answers which are here, even there's none of them, meaning I might have found something wrongly here. Should I punch it again, or you can punch it since you've already seen the right formula to use? Okay, please make sure that you, anyway, let me just do it in case. You should be confirming also as I'm punching. Be confirming so that I don't punch what is wrong, because dealing with writing and punching, just be confirming. Okay, so starting with the half-life for a first order reaction, we are saying that half-life of a first order reaction is going to be equal to natural log of 2 divided by k. So we've been told that the half-life for a first order reaction is 32 seconds. So put there 32, and that will be equal to natural log of 2 divided by k. To find the value of k, we are going to simply find the natural log of 2. The answer we divide it by 32. So natural log of 2, answer divided by 32. and that is going to give us a 0.02166. And then we have been also told that what will be the original concentration if after 2 minutes the reactant concentration is 0.06. So now for this one, that's where we come to the integrated rate law of a first order reaction, and we are saying that the integrated rate law for a first order reaction is natural log of the final concentration is equal to natural log of the initial concentration minus K multiplied by T. So this will be natural log. The concentration which we are finding is 0.062, and this is going to be equal to natural log of the initial concentration. That is what we're trying to find. Then minus K is 0.02166, and then T here is the time. Time should be in seconds. So 2 minutes, that is 120 seconds, right? Like that. So I'll start with this side, 0.02166, we'll multiply that by 120. The answer that we get is a negative number. I'm going to take it the other side so that I add it to the natural log of 0.062. So we remain with natural log of the initial concentration is equal to, if you multiply 0.02166 times 120, you're going to get uh, what number is that? Oh, I've even multiplied. This is where it's becoming wrong. Let me multiply that again. Accuracy. Okay, 0.02166 multiplied by 120. That is going to give us like a 2.599. You can confirm that. And then that number, is that the same one you found? Okay, we'll take it the other side and add it to the natural log of 0.062, and that is going to give us a negative 0.181318. So to find now the initial concentration of A, it will be e to the power negative 0.181318, because a natural log has got base e. 0.83. Okay, so meaning that is basically 0.84. Okay, so see, it was a typing error. So make sure that you are very careful as you get to write. So question number 9, which of the following is true of the electrochemical cell represented below? Look at what is happening. Electrons are moving from M, they are going the other side, entering into this region. So what will happen is that the reaction this side, this M is losing electrons to become M2 plus, which you can see in solution there. And then this N this side will be gaining those electrons to become N2 plus. If you can look at N here, initially the oxidation number is 0, is going to positive 2. So this is oxidation. So this one is moving from 0 to positive 2. Okay, this one is even an error here. This is a wrong reaction. It doesn't exist. This N2 plus that you can see in solution is going to be gaining 2 electrons to become N. Okay, that's what happens where electrons are going. There is a gain of electrons. So oxidation number is changing from positive 2 to 0. That is reduction. And then this one here is oxidation. So metal M is being oxidized. That is true. N2 ion is being oxidized. No. Metal N is being reduced. No. M2 are being M2 plus ions are being reduced? No. So the answer is A. Hope that makes sense. A chemical reaction that absorbs heat from the surrounding is said to be dash and has a dash delta H at constant pressure. Chemical reaction that absorbs heat from the environment is endothermic. So the possible answers is this one and this one. So these two can't be. And as dash delta H at constant pressure. So delta H is going to be positive when a reaction is endothermic. Because if it is negative, it means that the reaction is exothermic. So the answer is going to be A. 11. Calculate the change in enthalpy for the reaction of sulfur dioxide and oxygen. They've given us the reaction here. Change in enthalpy is given by the enthalpy of the product. Look, on the product you have got sulfur trioxide, two of them. So I'm going to say 2 times the sulfur trioxide, and that is negative 395.7. The answer that you get, subtract minus. You find the sum of the enthalpies on the reactant. You have got 2 sulfur dioxide and each is negative 296.8, and then plus you have got oxygen, and then oxygen is enthalpy. Every time you're talking about a diatomic gas or a pure element, its enthalpy is 0. 2 multiplied by negative 395.7, and then you subtract 2 multiplied by negative 296.8. So it's going to give us a negative 197.8. So it's going to be in kilojoules per mole. So this is B. You've seen the importance of signs, huh? Very important, because if you just found went direct and then you found positive, that's not correct. Which of the following has highest boiling point? Has highest boiling point. Okay, the first thing maybe to know is the trend of boiling point. Boiling point, we know that it is basically a point at which something changes from being a liquid to being a gas. Now, what will be the trend? You want to look at how much atoms want to avoid changing from being a liquid into being a gas. If you check in the periodic table, boiling point is going to increase across a period. So as you move from left to right, boiling point is increasing. And that is because there is an increase in intermolecular forces. Atoms become more held together strongly, right? The boiling point is also going to increase across the metals from left to right within a period because of their strength in metallic strength. Okay. So you want to go on the periodic table and look at this. Now we have been given all of these here are halogens. So sorry, not halogens, but inert gases. So I want to look at inert gases, or what's the other name for inert gases? You can't respond? Okay. So I want to look at group 8 elements and to see what trend do they possess when it comes to boiling point. So when you're comparing group 8 elements or the noble gases, the general trend in the melting and boiling point is down the group, decrease. So there's going to be a decrease in boiling point as you go down a group, meaning that as you go up, there's an increase. So there's a decrease as we go down. So the one with that is going to be smallest is going to be helium. And then as you get to go down, the highest is going to be like argon at the bottom. If you check in the periodic table, boiling point increases as you go down. Okay. So which of these has the highest boiling point? Yes, please. Okay, think of it generally as you go down, there's a reduction, there's a decrease. Do you get that now? Generally, as you go down in the periodic table, there's going to be a decrease. Okay. Question 13. What is a triple point in a phase diagram? When you have got a phase diagram is just a diagram that is showing how a compound is going to be able to transition in the three states of matter. Okay. Can talk about the phase diagram for water, for carbon dioxide, and for these others. In case of, let's say, water, you are going to see a line is going to go like that. You are going to have another one like that, and then like that. So in this region, water is a solid. Here it's a liquid, and then here it's a gas. At this point where water exists in all the three states of matter, that is what we call as the triple point. You're also going to have a critical point. So when you're talking about this change, this change of state from solid to liquid, we know that is melting. But specifically when you are the pressure here, because this one is pressure and then this side is temperature. When the pressure is 1 atmosphere, that is the normal melting point. So on any one of this line, water can melt, but at 1 atmosphere, that's a normal melting point. Okay. What is a triple point? A point where the temperature and the pressure conditions are fixed for all the three physical states. Point on the graph where the supercritical fluid is found. Now, supercritical fluid will be found here. You are going at the end. You are going to have a vertical line and an horizontal line here. In this region, this is a region where water is going to be found, or a compound will be found purely as a liquid and purely as a gas. That is what we call a supercritical fluid. So that's not the answer. The point on the graph where solid and gas are in equilibrium. The point where the sublimation takes place. Sublimation is any point here where the compound can change that from solid to gas. So a point where the temperature and pressure conditions are fixed for all the three states of matter. Okay, that's a triple point. Number 14. Seawater is dangerous to drink because seawater is dash to your body tissue and can cause you to lose water. I think the statement which answers the question is will cause you to lose water. You can only lose water if there is something that is more concentrated, because water wants to go to a region of high concentration, isn't it? So meaning that such a solution is hypertonic. Okay. Suppose the reaction A plus 2B producing A plus B2 occurs by the following mechanism. The rate law expression must be rate is equal to. So the rate law expression, rate is going to be equal to. When you are writing the rate law expression, you use the rate of a slow reaction. Okay, the rate of a slow reaction. And the slow reaction is this one. So therefore the rate is going to be the K multiplied by the concentration of A multiplied by the concentration of B. So this is this one here. The rate of the overall reaction is going to be equal to the rate of the slowest reaction. Calculate the equilibrium constant for the reaction of oxygen with nitrogen to give nitrogen dioxide at 423 Kelvin, given that delta G is positive 22.7. What do you want? Calculate the equilibrium constant. We've been also given the temperature there and also delta G. So what we want to find out is the relationship between delta G and what temperature and which one else? Equilibrium constant. Okay. relationship between delta G, equilibrium constant, and temperature. Do you know the relationship? Anyone? Nothing? Okay. Delta G gives free energy is given by negative RT natural log of K. So delta G, which is gives a free energy, is given there, which is 22, and this is going to be equal to negative R is the universal gas constant, and it should be given in the question. Let me see. I mean, it's given on top where there are those values. Okay, let me just go and check it out. Now, you need to make sure that you pick the right unit for G. So look at this. Your temperature is in Kelvin, and then what else have we been given here? Delta G is in kilojoules per mole. So pick something that has got Kelvin kilojoules per mole, because R is going to have a lot of units. You can see they've even given it a lot of units here. We want something that has got Kelvin kilojoules per mole, right? Like that. So joule per mole and the Kelvin. So you go for this one, 8.314, 8.3145. And then we multiply with the temperature. Make sure that the temperature is always in Kelvin, and this one is already given for 23 Kelvin, and then natural log of K. So what I'm going to do is I'm going to first start the other side of the equation. 8.3145, 8.3145. I'll multiply that by 4.23, 4.23. Sorry, it's not even 4.23, 423 I meant. The answer that we are going to get, we are going to divide both sides. So I'll say 22 over that answer that we get. And that is going to give us natural log of K being equal to negative 0.006255. Therefore, to find K is going to be e to the power negative 0.006255. And what are we going to find? Okay, so this is giving me 0.99. Again, okay, 0.99. This should be again just another wrong punching. Okay, I've seen where it's wrong. It says I didn't pay attention to this. Please, if it comes, please make sure that you pay particular attention. This can cost you, especially if the question came on show your work, because at least multiple choice you can see you have not found any answer there. Your value should never be in kilo. This value is given in kilojoules per mole. Should be in joules per mole. So delta G should be in joules per mole. So instead of 22.7, this should be 22,700. You multiply by 1,000, and that should be equal to negative R 8.3145, and then multiply by temperature 423 natural log of K. 8.3145 times 423. The answer that we get now, we say 22,700 divided by that answer. So that will give me natural log of K being equal to negative 6.454. And then now that's when we'll say E to the power that number. And that will give us like a 0.001, which in standard form, 0.001. What's the other value here? I've lost the value on my calculator. Hope has someone punched? What were the other values? 0.001 what? Yes. Okay, so the answer is C. If you express this number, I've not recorded the other values because I've lost the value that I punched on the calculator. But if you write this in standard form, the decimal point to move 1, 2, 3. So it will be like 1 point something times 10 to the power negative 3. And that's the one there. What is the pH of an aqua solution at 25 degrees that contains a 3.98 times 10 to the power negative 9 molar of hydroxide? Now I want to calculate the pH, but you've been given the concentration of hydroxide. pH is given by 14 minus POH. So what we'll do, this will be 14 minus POH is given by negative log. Please, this minus is part of the formula. That negative log is part of the calculation for POH. Don't confuse them. So negative log of the 3.98 times 10 to the power negative 9. So that's what we want to punch. What is that going to give us? Those with a calculator. Try again. Okay, let me try with my cash. So I'll start by punching negative log of, we've been given 3.98 times 10 to the power negative 9. That will give us 8.4. 14 minus 8.4, that is 5.599. Okay, so that is 5.6. So this is the answer here. Which of the following combinations cannot produce a buffer solution? Now, a buffer should be made of a weak acid and its conjugate base. Okay, weak acid and its conjugate base. Now, if you look at this one is a strong acid. So, definitely can produce a buffer because it's a strong acid. There are just about 7 strong acids that we have to know. There are just 7. The first one and the most common is hydrochloric acid, HCl. The other one is hydrobromic acid, HBr. HCl is the strongest. And then you have got hydroiodic acid, you have got nitric acid, you have got sulfuric acid, you have got also this one with the CO with a 3, and then it's a CO and a 4. When you just see these guys, they can't form buffers, these guys, because they are strong acid. A buffer should be made up of a weak acid and this conjugate base, even without looking at other options. Okay. Question 18. Which of the following okay, that's the same. 19. Hybridization of carbon atom in a carbon anion is hybridization of carbon atoms. If we say carbon anion, we mean that we have got a carbon atom that is negatively charged. A carbo cat ion is positively charged. Carbo anion is negatively charged. If you look at this guy, it has got an extra electron. So what does that mean? So in it, normally carbon is supposed to be bonded to four different things. And when an atom is bonded to four different things, the hybridization just count one of these is always an S. Okay? And then the others will be P's. If a carbon atom is bonded to only three things, just know that the one of them is always an S. The others are P's. If a carbon atom is bonded only to two things, just know that one of them is an S, the other one is a P. So that's why I've got sp3, sp2, and sp. So now can you tell me what is the hybridization of a carbon atom in a carbo and ion? Or is it that you can't you mhm, sp what? Why have you chosen sp3? Because it's going to be bonded to four different things, isn't it? Okay. Select the correct structure of 2-methyl propanol. 2-methyl propanol. Okay. So the correct structures, and this is going to be the last question. We'll do section B tomorrow and section C. 2-methyl propanol. I can write for you the structure. From the last word propana, meaning three carbons. Carbon number one, number two, number three. But because it ends in propanol, it ends in AL, it means that it's in an aldehyde. Meaning that an aldehyde is at the end of the chain, you have got a double bond with an oxygen. And then at position number two, you have got a methyl. So you have got a methyl. So this is a structure. At this end, you have got CH3. At this end, you also have CH3. At this end, you have got a carbon bonded to oxygen. At this end, you have got a carbon with one hydrogen. So if I start from this side, I'll write this as CH3, and then I'll come here, I'll write it as a CH, and then this CH, look, it is bonded to CH3, so I'll write that CH3 in brackets. And then we have got now this carbon. This carbon on here has got one hydrogen, but it is also bonded to an oxygen. So I can see that to be the formula. CH3, CH, CH3, CHO. So that is this one. Okay.